This is our 2.3 notes. You can see we just have the one objective today because today we're going to be learning all about objects that are falling and therefore they are still only experiencing one-dimensional motion. They're moving in one direction, down. But they are experiencing acceleration due to the force of gravity. So the nice thing about this is you never have to worry about looking for acceleration due to gravity in the problems because it's always going to be the same. So our objective today is just that you will be able to describe for me acceleration due to gravity, that you will be able to calculate it and use it in calculations using our same equations that we used when we talked about acceleration, but just using the value of acceleration due to gravity in the problems. So, falling objects experience constant acceleration. If we ignore air resistance, which we will a lot because we're physicists, all objects near the surface of the planet accelerate at the same constant rate. They accelerate in what we call free fall. This acceleration is due to the force of gravity. The symbol we use for the force of gravity is A sub g. So the symbol for acceleration with a small subscript of the letter G. On Earth, though, we just often use the symbol G instead.
What's the aiming?
Acceleration.
Oh, acceleration.
Yep. And on Earth, the magnitude of acceleration is negative 9.81 meters per second squared, or if you want it in feet per second, there that is too, but we're going to be using the meters per second squared version. Acceleration due to gravity is always directed downward. Even if the object is moving upward, the acceleration is still downward. I know that's kind of difficult to think about, but that's why we represent it with a negative, because it's always directed downward.
But something can't fall upward.
Correct. But when you throw an object upward, it's accelerating by slowing down, not by speeding up. So its acceleration is still in the downward direction. I know, like I said, it's a little tricky to think about. We're going to talk about it in a little more detail. It's very easy to think that an object that has more mass should accelerate more because force is equal to mass times acceleration. But you have to remember that objects with more mass also have more inertia, which makes them more difficult to move. So that greater inertia balances out the greater force of gravity, which means all objects near the surface of the Earth accelerate at the same rate. Okay, let's use an example to talk about acceleration so that we can hopefully make it make sense to your brain. When you throw an object up, it's going to continue moving for some time, and then it's going to pause at the top of its arc, and then it's going to commence falling back down to the Earth. Because the direction changes, it seems like to our brains, because of the way our brains understand things, that acceleration and velocity are both changing. This is not the case. Acceleration due to gravity is constant on an object at any time in this path. So if we're thinking about this object going straight up and coming straight back down, then at any point along that path that you check on it, its acceleration would be the same. It's going to be negative 9.81 meters per second squared. While the object moves up in the positive direction, the negative acceleration causes the velocity to decrease. The object slows down. Remember that acceleration is equal to velocity final minus velocity initial divided by time. So we have our initial velocity where it's traveling pretty quickly and our final velocity where it's traveling much slower. So it's going to be negative because of that. Okay? So you think about that. And then, so because our final velocity, so if we're traveling in the positive direction in this case, right? So let's put some numbers with this to like help it make sense, right? Like if it was traveling upwards and your initial velocity was, 20 meters per second, and then it's slowing down because it's moving against the force of gravity, then your final velocity was, say, only like 2. Okay, you do 2 minus 20. So divided by time, which is always positive, your acceleration is going to come out to be negative. So imagining that this is like our fake initial velocity, 20 meters per second, and our fake final velocity, 2, because it's slowing down as it goes up. That's going to wind up being a negative number, right? 2 minus 20, which then when divided by time, which is always positive, is going to mean that our acceleration is negative, right? So even though the ball is traveling upwards, it's slowing down, which means its acceleration is negative. It's traveling in the positive direction, but it's slowing down, so acceleration is negative. These numbers are, of course, made up off the top of my head and would not yield the correct acceleration due to gravity. They're just there to be an example. When the object is at the top, there is a brief moment where its velocity has reached 0 meters per second, but it is still technically accelerating downwards. It's still experiencing that force due to gravity. It's just its velocity has finally reached 0. But given a little bit more time, it will begin its journey down, moving in the negative direction. And that negative acceleration is now going to cause the velocity to increase. So the object is going to speed up. Okay. So we are now moving downward, okay, which means we're moving in the negative direction. So if we take that same equation we used before, acceleration is equal to velocity final minus velocity initial divided by time, okay? Let's say our velocity initial is 0 for the top of this arc, right? So we have 0. But our velocity final is now negative 20 meters per second because now we're traveling in the negative direction. So negative 20 minus 0 still comes out to be a negative number. When we divide it by time, which is always positive, we still get a negative number. So even though now we are speeding up instead of slowing down, our acceleration is still negative. So this is how the acceleration due to gravity is the same all the time, the whole arc. Okay? If I gave you real numerical data and you calculated it for at any point in the movement of this object, you would come up with negative 9.81 meters per second squared. When it's moving upwards, it's slowing down, which causes the negative acceleration. When it's moving down, it's speeding up, but it's moving in the negative direction, so the acceleration still stays negative.
You should repeat that because I'm just going to summarize it a little bit.
As a result, the acceleration of a falling object is always a straight line on a displacement time graph. It's just going to be, because acceleration is constant, you remember, it's just going to be a nice...
That's going to mess with me though.
Yeah.
Because it's supposed to be going up, staying, and then going down.
Nope.
Oh no.
Yep, because we're talking about acceleration here on a displacement time graph, then it's just going to be a straight line. Oh, hang on, I'll pause and let you.
Nice. It's going to be exactly a page.
Our practice problem is we're going to talk about the famous Gateway Arch in St. Louis, Missouri. It is 192 meters tall at its highest point, and we have stunt woman Sally, who is jumping off the arch, hopefully attached to some kind of protective equipment. She's going to land in 6.4 seconds on the safety pad at the base of the arch. Okay, first we're going to calculate her average acceleration, and then we're going to use our lovely equations from the last chapter to solve for her final velocity. Okay, so we're going to start by determining what do we know. So what information do we know about this situation?
192 meters tall.
Okay, it's 192 meters tall. Normally we would represent that with a change in x, but since we are working on the y-axis today, we're going to call it a change in y instead. And because she is technically falling downwards, it's in the negative direction, so we're going to give it a negative symbol. 192 meters.
6.4 seconds to
Yeah.
land.
Our change in time is 6.4 seconds. Time cannot be negative. And then we do have one velocity.
We know the gravity one, which is negative 9, negative 1.
That's an acceleration, and that's what they want us to calculate. So
Oh.
they want us to try and calculate it on our own. So the velocity we know velocity initial because she's not moving at the start, right?
Mm-hmm.
When she's standing on the arch, her initial velocity is going to be 0 meters per second. So if we're solving for acceleration, that's the first thing they want us to do. They want us not to trust our textbooks and instead calculate it ourselves. Then we are going to go ahead and pick an equation from our list of equations that would allow us to solve for acceleration having only a change in distance, a change in time, and an initial velocity. Can you identify an equation that would work for us?
I think I need to write these out better. I totally can.
The equation I would use is our lovely change in, you have it written as change in x. I have it here, change in y equals velocity initial times change in time plus 1/2 acceleration times change in time squared. Okay, what we have to do is we just have to rearrange this equation to solve for acceleration instead of solving for change in y. If we did all the work to switch this around and manipulate it, we would wind up with acceleration equaling 2 times change in y minus velocity initial times change in time divided by change in time squared. So that's just me manipulating the above equation to get acceleration on its own.
Can we plug and shove it? Since that's how I do it.
Absolutely. We can definitely do that. So instead, let us just plug in the information that we have. So we have negative 192 meters. We can eliminate this portion of the equation because our velocity initial is 0, which just leaves us with 1/2 acceleration times our change in time, 6.4 seconds squared. So to begin with, we'll square 6.4 and I come out with 40.96. Is that what you get?
I plugged half times 6.4 squared.
We'll leave the half alone for now.
No wonder I didn't write it down. I was like, that's wrong.
And 40.96 seconds squared now. We're going to divide both sides by 40.96 seconds squared. And that means we'll be dividing negative 192 meters by 40.96 seconds squared. And we should come up with, I'm running out of room to write here, so I'm going to do a little bit of erasing of my board. But what we should wind up with is 1/2 acceleration is equal to negative 4.6875. We're going to want to go ahead and take both sides by 2 to get rid of that half. Oh, and sorry, we did wind up with a unit of meters per second squared, which is how we know we're on the right track. Take this times 2, and we come out with acceleration being roughly negative 9.375 meters per second squared. If we look back to our original, we should only have 2 significant figures, so we will round this to negative 9.4 meters per second squared. So there's our lovely acceleration, which tells us, since it's not exactly 9.81 meters per second squared, she must have had some sort of safety equipment, right, to decrease her acceleration ever so slightly, though I'm really honestly not sure if that's enough decrease in acceleration to save her should she fall that distance with no other protective equipment. But something must have slowed her descent, either air resistance or some kind of safety equipment.
A bird.
A bird.
On the way down.
Now that we have an acceleration, they want us to solve for velocity final. So, given what we knew before, we should be able to use the equation velocity final is equal to velocity initial plus acceleration times change in time. So if we started at 0 meters per second and we have an acceleration of negative 9.4 meters per second squared times our change in time, which was 6.4 seconds, then we should end up with, I get negative 60-ish meters per second. And we want it in 2 significant figures, so we can either put a decimal point at the end here, or we can put it in scientific notation and make it negative 6.0 times 10 to the 1 meters per second. And there's our velocity final. So started moving at 0 meters per second and ended at 60 meters per second in the downward direction. Yeah, sometimes I think it would help if we wrote it like seconds over 1. It would help us see that those seconds cancel out and we're left with meters per second. All right, that is the end of the notes for today. Your homework is on page 63, and I'm going to have you do questions. Let's just do 1 through 6. There are some of them that are not super hard, so we're going to do 1 through 6.